Take a moment to think about all the information moving around you right now. The music streaming into your earbuds, the Wi-Fi signal connecting your laptop, the light hitting your eyes. Every single piece of that information is being carried by a wave. A wave isn't matter, it's just a disturbance, a vibration, and efficiently transfers energy from one point to another without moving the physical stuff it travels through. Understanding the basic properties of these waves is the foundation for all modern technology. Waves generally fall into two categories. Mechanical waves, like sound or a ripple in a pond, require some form of matter or a medium to travel. If you take away the air, the sound stops. But the most important waves for information technology are electromagnetic EM waves. These include light, radio, and X-rays. EM waves are unique because they don't need a medium. They can travel perfectly through the vacuum of space, which is how we get signals from satellites. Most of the waves we'll be discussing, especially light and radio, are transverse waves. Imagine shaking a rope up and down. The wave itself moves horizontally across the room, but the disturbance, the rope moving, is vertical. The motion of the disturbance is perpendicular to the motion of the wave. The highest point of this kind of wave is called the crest, and the lowest point is the trough. In contrast, a longitudinal wave vibrates parallel to the direction of motion. The best example of this is a sound wave. When you talk, you push air molecules back and forth. These molecules bunch up, creating areas of high pressure called compressions, and then spread out, creating areas of low pressure called rarefactions. The wave moves forward, and the air molecules also vibrate back and forth in that same direction. To start describing a wave mathematically, we need three key properties. First is wavelength, symbolized by the Greek letter lambda. The wavelength is simply the physical distance from one part of the wave to the next identical repeating part, usually measured from crest to crest. If you could take a snapshot of a wave, the wavelength tells you how long that repeating pattern is. Next, we have frequency, F. Frequency tells us how often a wave repeats itself. Imagine watching a surfer. Frequency is the number of wave crests that pass the surfer every second. A high-frequency wave means a lot of cycles per second, and we measure this in hertz. A 100 hertz wave means 100 wave crests pass a point every single second. The third property is wave speed, V. This is exactly what it sounds like, how fast the energy of the wave disturbance moves. For mechanical waves like sound, the speed depends entirely on the medium. Sound travels much faster in dense materials, like steel or water, than it does in thin air. For all electromagnetic waves, like light, the speed in a vacuum is a constant, known as the speed of light, c. Now for the mathematical core, the wave speed equation. This fundamental formula connects the three properties. Speed equals frequency times wavelength, or V equals F lambda. This equation holds true for every single type of wave, whether it's a ripple in a cup of coffee or a massive gamma-ray explosion from a distant star. It's the master key to wave behavior. The wave speed equation reveals a crucial relationship. If the speed v of a wave is constant, which is often the case in a uniform medium, then there must be an inverse relationship between frequency and wavelength. Think of it like a seesaw. If you increase the frequency, the wavelength has to decrease to keep the speed balanced. High-frequency waves are always short, tiny waves, while low-frequency waves are long and spread out. The electromagnetic EM spectrum is perhaps the most important concept in information technology. Every EM wave, from radio to light to X-rays, is fundamentally the same. It's just energy vibrating at different frequencies. Since all EM waves travel at the exact same constant speed, c, in a vacuum, their only difference is their frequency and, consequently, their wavelength. The spectrum simply maps out these differences. On one end of the spectrum are radio waves. These have the longest wavelengths and the lowest frequencies. Because of their long wavelength, radio waves are excellent for broadcasting. They can bend around large objects, like buildings or hills, allowing them to travel great distances to reach your car radio or home antenna. Move slightly higher in frequency and you hit microwaves. These waves are crucial for modern communication. They are used by cell phones, GPS systems, and satellite communication. Microwaves can carry much more data than radio waves because they have a higher frequency. They are also, of course, used in your microwave oven to rapidly vibrate water molecules and heat food. Just below the visible spectrum is infrared light. We usually feel this as heat, as it's the radiation given off by warm objects. Infrared is used in night vision goggles because it can sense the heat signature of objects. It's also used in short-range applications, like the tiny beam that sends a command from your TV remote control to the television set. The only part of this vast EM spectrum that humans can actually see is the tiny window we call visible light. It ranges from red, which has the longest wavelength and lowest frequency, all the way to violet, which has the shortest wavelength and highest frequency. All the colors travel at the same constant speed, c, but their different frequencies are what determine the color we perceive. Visible light and near-infrared light are revolutionary for modern internet access. Fiber optic cables are hair-thin strands of glass that transmit data using rapid pulses of light. Because light has such an extremely high frequency, it can carry an enormous amount of data, far more than electrical current in copper wires. This is how the backbone of the internet delivers blazing fast speeds. Waves can carry information in two ways, analog or digital. An analog signal is a continuous wave that varies smoothly, like a sound wave recorded directly onto an old record. A digital signal, however, is composed of discrete pulses. It's either on or off, representing the ones and zeros of binary code. Digital is superior for information technology because it's much more resistant to noise or static, making the data clearer and more reliable. When you send a text message or stream a video, that information is converted into a string of odd dollars and $0, known as binary code. These bits are then translated into the digital signal. A wave pulse is a 1, no pulse is a 0. Engineers also use compression techniques, like those used for MP3s or JPEG images, to reduce the number of $1 and $0 needed to represent the data, making the transmission faster and requiring less energy. No matter how fast technology gets, all information transmitted using EM waves, Wi-Fi, cellular, satellite, is fundamentally limited by the speed of light, c. While 300 million meters per second is unbelievably fast, it's not infinite. This is why when you video call someone on the other side of the world, there's a slight, noticeable latency or delay. The signal has to travel all that distance, and even at the speed of light, it takes time.